Well, I've got us right here at 12 noon, Brady, so it's time to get going on our next Lunch and Learn. Folks, we've got Brady Reisch with us today, and he's going to be taking us through one of the Stonex base stations and how we use them with drones. And so without any further comment, I'm just going to turn it straight over to Brady. Brady, the floor is yours.
Thank you very much, Douglas. And welcome everybody for coming to yet another Lunch and Learn. We do provide these every Thursday at noon. We do have a few coming up that we'll talk towards the end here about. But with that being said, let's go ahead and just jump right on in and talk about the Stonex. So the Stonex system, we're talking specifically about its integration with UAS and how it works with the drone itself. So just a little bit of back information, so we have a little bit of context here for everybody, is we have a couple different modes that we can fly our UAS, our drones. So the first being single or non-corrected data. What will happen is when we fly our drone, we are using GPS with most drones. And with the GPS, we can have an error of about 3 meters. So we're introducing that error because we're looking at what we call a single constellation, which is going to be the GPS satellites. That being said, when we have an RTK capable drone, we are then able to add additional constellations to have higher precision. So rather than using a single constellation, we're using multiple constellations such as Galileo, GLONASS, Baidu, QZS as well. But in this case, we're adding more and more satellites to give us a higher level of precision to where the drone is flying in real time. So this data means that we're not being corrected. We are not looking at a base station or at an entropy network. This is simply just having access to all of those different satellite systems. We are increasing our accuracy off the bat. Now, that being said, when we are able to utilize the GPS, Galileo, GLONASS, and Baidu systems, those other constellations, we can then take that data and post-process and bake that into our imagery, which gives us an even higher precision. The way it does this is that the drone itself is capturing the location of all of those satellites in real time, stores it, and then we are able to take that file and then post-process through a separate program in order to give us a even better precision here. So this is going without using any what we would call ground control points, which, again, if you're new to our Lunch and Learns, may be a foreign concept, but that's something that we will cover again in some of our future videos. But with PPK or post-process, we were able to dial in where the drone was versus where something else was, such as a GNSS base station or a CORS network. So these CORS stations are capturing where the satellites are, and our drone is capturing where the satellites are. And what we're going to do is we're going to fix what our drone had, because our drone has lower precision than a base station would, because we're actually moving around consistently. So we are going to fix it to what the base had, and this is all done post-process. Now, this then also leads into, with an RTK drone, which I had mentioned a little bit earlier, is that RTK is the same process, except we're doing it in real time. Rather than going out to a separate provider, we are able to run this data instantly, right here, right now, which gives us a higher precision, which means we have a little less work on the back end for post-processing. Again, we're using the GPS, Galileo, GLONASS, and the Baidu constellations in order to fix the position of our drones. In order for this to happen, we need to have some sort of a static base capture. So this will be, if you think about like a surveyor, when someone goes out with a pole and with a GPS head on the very top, we are capturing a very specific point over the entire duration of this flight, which means that surveyor that's holding up that pole stands in the exact same spot, right? So what we would traditionally do is put this onto a rod and a bipod or even a tripod, and it would hold steady from beginning to the very end of that flight. And when we have that station, it is collecting data and understands where the satellites are, and then it's going to, in real time, communicate through the controller to the drone to give us those correctional coordinates and the corrected data. So in order for this to happen, we have to have a very specific set of pieces, which are going to be that the actual unit itself that we're going to be using has to be in base mode, where it's capturing and it's static. It can't move at all. That also has to broadcast a Wi-Fi signal of some kind or have some sort of an internet access. So this is so that it sees what it has and it wants to broadcast corrections to something else, to which then goes to the remote up into the drone. So our remote is connected via Wi-Fi to that base station. And in order for the drone to understand the data that's being received from that base station, we're using the RTCM3 protocol. It could be 3.1, 3.2. There's a couple different sub protocols that we can use. So we just generalize and say the RTCM3 protocol data. So when we have this, as long as our drone is enabled and capable of receiving that real-time kinematic correctional data, our drone will be fixed. And this is when we're getting very high precision. Now, what I do want to mention here is some manufacturers may tell you if you have RTK, you don't need ground control points. That is not true. That is all marketing hype. You will always need some sort of ground control to validate and to correct that data. This gets us really close to being able to process that data accurately, but it's not so precise that you can get away with not using some of the other pieces. If you talk to any surveyor, you always have to have some sort of control and some sort of validation. If you don't have that, then you can't verify that your data is as accurate as you claim. So what we want to dive into is, where does this really fit in? Right? How are we going to utilize this? So the GNSS, right, which is allowing us to look at the other constellations, not just GPS. We're looking at all the constellations here. The standard GPS, again, gives you about 3 meters of error. When we start adding in urban environments, we can add in what's called multipathing. And what multipathing does is think of a signal that's bouncing between the buildings and then goes into your phone. So you're driving down an urban center and it says, hey, turn left now, and it was half a block behind you. This is usually what the cause is the multipathing, thinking that, hey, I'm giving you updated, corrected information, but the timestamps are not correct, and it's been modified because it's been bouncing around from usually reflective surfaces or hard surfaces. So we want to correct for the GPS error by adding in the other constellations to dial that back in. Now, you will not always get 3 meters of error. This is a maximum error in ideal conditions. But again, it can get worse from there by using other pieces such as multipathing. When we use GNSS antenna specifically for photogrammetry, what we're doing is we are telling the drone exactly where it captured a picture, rather than the drone thinking, hey, I should be over here, but I'm actually should be over here. We are forcing all that data to say, no, you should have been over on this side. What this does when we process our data is we get far greater data, and our processing software is much more efficient at processing that data, which means that as we're processing, if you do it locally on your computer, it takes less resources and less time for that to actually be processed, because it says you've already been corrected, and I don't have to kind of fit all these images in the right location in order for it to stitch together appropriately. On top of this, we also have access to control the pitch, roll, and yaw. So what we're talking about is when our drone is basically pitched nose down, we're pitching forward, our yaw side to side, and our roll as we're rolling right and left. We have all three of these control surfaces that, if our GPS data is wrong, or if the photogrammetry software stitches it in incorrectly, it will change, and you'll see basically the whole model at an angle and tilted and rotated in the wrong orientation. So by using GNSS, we're adding in additional constellations to help fix the pitch, roll, and yaw. In addition, we're going to be using ground control points of some kind in order to validate that this doesn't happen. So then, what does GNSS have to do with LiDAR data? LiDAR is inherently arbitrary. And what I mean by this is that as we're scanning our data and getting all of our points on the ground, we are not receiving geospatial information. It's not embedded into the LiDAR data. So most LiDAR software processing programs will actually use PPK, or the post-processing kinematic, to tie in the trajectory of how the drone was flying, the camera orientation, which just means which direction the camera is facing. Is it forward? Is it down? Is it side to side? And so it's building all that together, but it also includes the geospatial location data from the antennas. So with the processing software, this is why usually if you're looking at LiDAR data, you can't get it immediately off the drone and here's your LiDAR data. No, it has to post-process to fix and correct and put a location on the earth to that LiDAR information. So this is something that we can talk about. If you're more interested in how some of these systems process, make sure to reach out and let us know. And I'm sure we're going to have some future lunch and learns about this specific topic. So that being said, let's get into what some of these systems look like. I've picked 3 systems here that I want to talk about. So primarily, again, this lunch and learn is about the Stonex, but I want to explain what some other people might be using and why we might want to use one over the other. So the first one is the MLID RS2 system. This is a fantastic system for entry level. It is a very low cost. But what happens is there's a couple of things that we're going to be lacking with some of these products, such as the MLID system. Because the price is so low for a lot of this, there is absolutely no support from MLID whatsoever. All of the support comes from the dealers and from the community. So by cutting a lot of the costs, they're able to bring that down quite a bit. But we can see with some of the accuracies here, our horizontal accuracy, and this is taking the best specifications from each of these sensors. So just be aware that environmental concerns, weather concerns could impact what we're talking about here. But our horizontal accuracy is about 4 millimeters, our vertical accuracy about 8 millimeters, and our data capture rate is at 10 hertz. I want to stop and pause and talk about what I'm talking about with the data capture, with the rate. As we're talking about these and we see 10 hertz for the Reach system, we're talking about this cycles where we have 10 different pieces of information or refreshes 10 times every second. That sounds incredibly fast to the human. There's sounds like there's no problems here. However, what happens is we have less data that we can pull from, right? Less data within that same 1 second time frame. So with the MLID, we're sitting at about 10 hertz. The Trimble 12i system, this is very popular. Trimble is very large. We have a horizontal accuracy of about 3 millimeters. So we're about 1 millimeter better there. Our vertical accuracy is at 3.5 millimeters. So we are under half of the vertical accuracy of the MLID system with the Trimble. And the data capture rate is about 20 hertz, right? Or up to 20 hertz. So we're receiving 20 packets of information every second over the 10 packets per second with the MLID system. And we're getting better vertical accuracies and better horizontal accuracies. And then last but not least here, we are also using the Stonex S980 Plus. This system has a horizontal accuracy of 2.5 millimeters, so just a little bit better horizontal. We have the same vertical accuracy as 3.5 millimeters. And the data capture rate, we're sitting at 50 hertz, so 50 different packets every second. So we're receiving that data very, very quickly and very accurately using the Stonex system. So diving into the specifications for the S980 Plus is that we are looking at the GPS, GLONASS, Baidu, Galileo, QZSS. So we're looking at all those different constellations to give us a higher precision. Again, we're sitting at about 50 hertz, so 50 times every second, we're gathering more information. This system has 32 gigabytes of internal memory, which means that we can go for days and not have problems. Ideally, my suggestion is don't store more than 1 day without backing it up somewhere or copying it to some other storage location, just for safety purposes. But we have a lot of data to be able to play with it with that internal memory. This also includes a 60-degree tilt compensation. So if we tilt and move it around, we can go up to 60 degrees side to side and actually be able to pick up that point on the ground that we're sticking that pole into. We have a 5-kilometer range in urban environments. So this is very far distance if we want to daisy chain or add pieces in or have one talk to another. And we're also looking at about a 15-hour working time. So this will be plenty if you're going out all day to fly your drone. Likely it'll last you for about 2 days without a charge in most cases, because you have to tear down and set back up. So you've got less than about 8 hours, 1 or 2 days. But overall, this will last a very, very long time with this system. So we like to use this system because it is a good alternative to some of the other pieces or some of the other systems that allow you to broadcast that wireless signal and have the N-trip or the drone basically talk to the base station over the N-trip or the RTCM3 protocols. So this system is, while it might be a little more expensive than like the MLIDs to get into, it's much more robust, and we also have additional support. It's not just going to be from dealers. We have support from Stonex themselves. So that's huge. So we get better accuracy, we have better support, and it is a product that is really built to do a very specific thing. And it also happens to work with all of our drone systems. So this is one of the big things that we love about the Stonex systems specifically. So with that, we're running just a couple minutes for questions here, and then we will go ahead and wrap up and let you guys get back to your lunch today. And Douglas, do we have any questions coming through yet?
No problem. Any specific questions yet, other than we had one on Facebook just a little bit ago. Does LiDAR PPK frequency really matter?
So yes, the LiDAR frequency does matter, and here's what we're going to talk about this year. With the LiDAR system, most LiDAR processing softwares will require the hertz to be 1 hertz intervals. So we can't have less than that. We need to have basically one frame every second for it to update with LiDAR. Now, as that happens, remember how we're talking about the MLID having 10, the R12 having 20, and now the Stonex having 50 hertz. What that allows the system to do is it will pick and find the best packet that has come through in order to utilize and post-process that data. So yes, having more hertz available to us is great. Just be aware as we go through and post-process, it will modify that and change it to 1 hertz as it's processed through those other programs.
Well, that's all we've had, Brady, so far. Is there anything you'd like to add before we wrap up is the word I'm looking for, before we wrap up our stream for the day?
So I think we've pretty much covered everything. If you do have any additional questions, make sure to reach out to the LiDARPros and let us know. We're happy to assist you and give you any information on any of these other products. We support many different types of products. This just so happens to be our favorite for this time is going to be the Stonex system. But make sure you reach out to us and ask us any additional questions after the fact. I know this will be posted on YouTube as well.
Folks can see that myhelp@lidarpros.com email address just down below here, and so they can reach out via the myhelp. Folks, if you'll look in your chat there, you'll see the next up and coming Lunch and Learns. So I think until next week, we're really happy to have had you present this information on the GNSS products, Brady, and we look forward to seeing the next chapter in this particular topic. So until next week, folks, thanks for tuning in. Be safe out there.